So Jim's going to start off, and then when he gets bored, transfer.
So this is the part of the conference where you're actually supposed to have your last time stop while other people are talking. So just to get a sense of where people are, I want to start with a quick survey. There were some instructions sent out before this tutorial before the meeting, and I'm curious to see a show of hands who has successfully installed the LSST software stack.
What version? What version?
Let's start with any version. Any version. All right, the latest version, 12.0.
What I meant was the GitHub or the Anaconda version?
Either from source or Anaconda. The rest of as long as you've got it installed, it shouldn't have any of those.
That's the one.
Yes. Anything moderately reasonable should be fine for all of this. All right, who has downloaded the example data, the small piece, the example1.fix? Who's downloaded that one? All right, got a fair number there. The instructions for this are linked from the conference website if you want to be real quick. You can probably still download the fix files. There's not enough people who will be doing it once that it will overload the server. Who has downloaded the larger chunk, the CIHC tarball? Who has downloaded the larger piece of example data? The folder I pointed you to has two things. One of them is big, the other one is small. Well, I shouldn't try doing it while you all are. So, we're going to start off with, I'm going to just introduce you to sort of a written tutorial that you can follow on your own time for the larger data set. If you don't have a larger data set right now, don't worry about it. The important thing is that you find this page, and if you're interested, you can go through it on your own, maybe this week, maybe later. If you do it this week, feel free to find me during the coffee breaks and ask for help if you get stuck somewhere. This is not something I want to try to go through live because it involves some processing steps that will take 5 minutes, and then it's boring if we just sit here and wait for everyone's laptops to process something for 5 minutes. But this is the URL you can find this at. That's dmtn-023.lsst.io. Let's see if I can't zoom that in. Hopefully you can all read it. There may have also been an email sent out to meeting attendees where you can find this link. So what this will do is you'll set up the software stack as usual. The installation instructions should cover that. You'll pull out this CIHC data set. We'll sort of set up a basic repository, and we'll start running the basic LSST processing pipelines. Now, these aren't the eventual processing pipelines we'll use, but they're basically the processing pipelines we're using for the hybrid Supreme Camp survey and Super. So they're pretty much state of the art. And this is a small-ish data set that's still 4 or 5 gigs, I think, that will sort of get you just barely through all the steps. This kind of processing where you can use the command line tools depends that you have what we call an OBS package already ready. So an OBS package is a piece of code that sort of defines an instrument or on a telescope. We have one for hybrid Supreme Camp, we have one for DECCAM on CTIO, we have one for MEGACAM on CHHT, and a number of cameras. I believe some people here may have actually written some of their own OBS packages. But you need one of those in order to process data through these paths. And so we're going to focus, this document focuses on HSC, and if you're interested in this, even for cameras that are not HSC, I encourage you to go through this little example so you can see kind of how it's supposed to work on a camera that's already well set up. And I'd be happy to help people with this. We probably couldn't get another ops package for another camera up and running during this meeting, but we can get you started, and if you're willing to work with people remotely, we can help you through that process. There have certainly been distributed ops packages as well. I think that's about all I'm going to do for this introduction. This is not, as I said, something we'll go through live right now. Robert's going to take most of the rest of this session to walk you through processing sort of generic data that hasn't been well characterized with one of these ops packages, and doing through some of the simpler steps and seeing how the code actually looks. If you want to get started on this and you think you can do it, right now before Robert does something else, you can get started and I can come help you later, but I'll send it to Robert at this point.
Okay.
Remove your laptop.
Thank you. Okay, so it wasn't exactly clear what would be useful. So what I did was to take Jim's example image, which
which is one CCD from Hyper Supreme Camp, one 2K by 4K chip. It's from some early data, and it's I think 30 seconds, so it's really quite shallow. It's actually around 15 or something. So it's really a pretty junky piece of data. And, well, it is. It's engineering data, that's why it's public. As I was saying in the previous session, we're going to release 100 degrees of GRIZY data in February. I'm now waiting for this machine to acknowledge that I exist. It's doing things. You have the power here. Okay, I'm going to get better resolution than that. It's probably good enough. So, what I was proposing not doing that was somewhere here. Yeah. We just sent you around this URL. This is a URL to GitHub, and this is some code that I wrote mostly on the plane coming here instead of sleeping. So it's probably a mistake. To poke at a particular unfixed file. In fact, the file example1.fix. So what I thought I would do is I will run through one of these Python notebooks. If you've got the stack and LSST code initialized set up, then you should just be able to say IPython Jupyter in the directory. If you check out this URL, which you will have sent in your email, copy that file, which is the example file that Jim referred to earlier, into that directory. I didn't put it into this debug. And then type IPython Jupyter. You should get at a page that looks like this, except for GUI. So this is then a set of 1, 2, 3, 4, 5, 6, count them, 6 notebooks. And my plan was to run through this one. I'm going to ignore this one. This one just pokes around inside some of our data structures. So if you're interested, you can do that. And then I'm going to leave you alone, on the tender mercies of Jim and Mario, who's just trying to leave. And Merlin, whose name I got right rather remarkably, is waving at you. And anybody else who feels like being helpful, to work your way through some of the others. And in the README, it says this, that this is an exploration of what the vendor does. It's not all that interesting in this data because it's not really very deep. So the objects are reasonably well separated. I talked about this, I'm going to run through this. This shows you how to check out, actually from GitHub, compile, import, and run the program cheat code. Then overlay the appropriate outputs. This pokes around a little bit inside the spread function estimation and shows you how to switch from using a not very good variant of the code I wrote for the SPSS to running an interestingly adjusted version of Emmanuel Bertin's PSFX, which involved casting pointers to character and pointers to struct way down in the C. You can't tell that. Here's an example of switching which PSF estimation code we're using. We're not going to use either of those in production. Those are the two we're mostly running now. And then here's an example raised by Richard and Marn earlier, which says, when I want to only find bright things, I don't want to find lots of faint fluff around other things. And I tuned a couple of parameters here to deal with that. So, if you can ignore me now, you probably are already, but if you're not, then, and if my laptop comes back to life, it's possible, I'm going to run through this notebook. You can run through this yourselves instead of listening to me. So here we go. So if you haven't used Python notebooks before, they're a really neat way of interacting with Python. And in fact, the user interface to the LSST database is going to look roughly like this, where you will be running this in a browser locally, and the data will be remote. That's actually a very nice way to deal with large data sets. So it's a technology that's worth learning. It used to be called IPython, I still call it that. Now it's officially called Jupyter with a Y, which looks really bad, if you ask me. Nobody is going to ask me. So, this first cell, which I will now execute, just set things up. It imports NumPy, it says I want inline plots, and it loads Matplotlib. Nothing there is SPSS, that's the wrong one, LSST specific.
Robert?
Yes?
Where is example 1.fix?
Jim sent around that URL a few days ago.
It's linked from there's instructions for tutorials on the conference website, and it's linked from there. It's a Dropbox link.
Okay. You mean, Merlin, that you didn't prepare this tutorial? Okay. You'll have time to learn about that. And then, this is loading some LSST code. This first line is an embarrassment I haven't got it yet. This is loading the AFW, that's the application framework, don't worry about it. It's just basically data structures that know about images and point spread functions and things like that. So you can think about this as boilerplate if you like, but we have to run it. And then this is loading the code that does bigger things. So this stuff up in here defines things like how to read an image from disk, how to convolve an image fast using a GPU optionally, though I don't think we compiled that in. This does things like point spread function estimation. I guess I'm going to have to run it there, I should delete it. Given an input catalog, a reference both metric and asymmetric catalog, get the WCS, get the 0 points. This says find objects. This says deblend objects. And this says go ahead and measure them. And it's called single because it's measuring on a single image. So these are the higher level units. And those are what I'm going to use today. Then keeping going, I will load a front end, in this case a DS9. This is also working around the bug. I forget what the issue number is. I filed it today. So that's just boilerplate to get going. And I could have hidden that behind a file you didn't see. But I was exposing more of the insights. Okay. This is a more interesting block. So what are we doing here? We're saying, I want to build an output table. You can think about that as being a fits table. It actually, I'm going to write it to fits at the end. Internally, it's just a set of columns of data. And it says, make me the smallest possible, most boring output table that Jim can think of. Which basically, I think, has an ID and an X and a Y. Is that right?
Already there.
Already there. An X, that's right. And then we say, I want to have a way to save some metadata. Okay. Then here is a pattern that you will see again and again as you go going. It says, here's a constructor, so that's a make me an object with this schema and return me a task. This one's a bit more complicated. It says, make me a configuration object. Think about that as a parameter file, a very large and complicated parameter file. And in fact, Jim will show you that we normally load these without seeing it from exactly parameter files. But I'm doing this interactively now. And then I set a parameter, which is the number of PS iterations to 1, because that should have been the default, but it wasn't. So I had to do that, and then I passed the config in. This one doesn't modify any output, so I don't have to do it. This one says, I pass in my table schema, and probably this task is adding more things, adding X's and Y's and errors. So we're basically adding columns to an output table as we go through. And then I do the same thing for the blender, and I say, if true, so I run this line, I'll run the second one later, build me a measurement task. So now I've got a bunch of things sitting around in memory that are capable of processing things. So now let's do something. So what have we done here? This is, let's say, basically a bug, don't worry about it. Here I say build an exposure object. This is basically an image, a mask, a variance, a WCS, a calibration, a PSF. But we don't know most of those things now. So think about this as just an image. So it's now been read into memory. I can look at it at this point. I will if you like. So we're using at the moment DS9 as a backend. I don't like DS9 any more than any of you do. That's the way it goes. And I have read into memory a 2K by 4K image from, in this case, from HSC. So this is a Hanamatsu 200 micron thick deep depletion device, if you care about such things. And I've in fact overlaid a mask plane. We skipped the whole instrumental signature level. This is already flat fielded, assembled, debiased. There are actually 4 readout amplifiers here. And I've also labeled the saturated pixels. I just wanted to skip that. I could have done an ISR task, instrumental signature removal task, then I would start with the raw data. That didn't seem very interesting, so I didn't do it. Okay? So delete that. So now create an output table. Do that. So now I say, given the schema, the list of columns I might want, make me a table with no entries in it. So every time I measure a source, I'll add another row to that table. So essentially I'm building a big two-dimensional table where each row corresponds to an object, and each column corresponds to X, Y, PSF flux, aperture flux 2. And this says, make me an empty one of those. And keep it going, doing all the boring bits. Now we can actually do some work. And if you did that, and if I had a window where you could see it open, you'll see it start spitting out some output, standard output. I didn't bother to attach this to a database or to a log file or anything like that. So there's a logger, and what we did was we went through and we said we identified some cosmics. I found 200 sources to 50 sigma. I resubtracted the background after object detection because I've masked things out. I measured 200 sources with outline of the blender. I measured the PSF. I found 134 candidate objects. I used 86 of them. I built a 37 by 57 PSF with sigma 3 pixels. That's 0.168 arcsecond pixels, so 3 times 17, I can't do it, 34, 51.5 times 2.2. This is 2.3 arcsecond C. Sorry, 1.2 arcsecond C. It's pretty bad. 3 times worse than the C. That's just what we got. And then I went back in, I found some more cosmic rays, now I know the PSF, and I remeasured it. So that's what happened when I ran this one line. If I now say, look at the PSF, I'll go back to that later. I've now got a spread function measured, and I'll go in, I'll do a detection. Don't know why that took so long. Oh, it's because I haven't finished So I can now go back in and just have another look at that image. This one. MTV stands for Morella TV because Jim Gunn and a fourth system on the 200 inch when we first put a CCD on the sky had an image processing system called Morella, named after Morella Frady, his favorite soprano. That's where the M comes from. I left it in that for 30 years. Jim gets the credit or lack of credit for that. And now we'll display the same image, except this time I've added a bit mask for all the detected pixels. So this exposure object is carrying around not only that I've got the pixel values, but also in fact a variant, which I'm not showing, I can show you the variants, and also the masks. So we've gone in and we've detected things. These are the pixels above threshold, which in Sloan I called OMS masks, and I renamed them as footprints for Panster. We've kept that name in LSST. So having done that, we can run the blender. And if I go back in that ran, and I look at my here, it said deblending 798 sources. Out of 798 sources, 124 were deblended, creating 466 children, total 1,144. So we've now detected 1,144 objects on the CCD. So let's go in and measure their properties. Now let's run that. Boink, boink. Okay, that's done. So we've now filled out all the rows. This is my table of objects, and I can now write it out to disk, and then we'll start poking at what's in there. So I'll write that to disk. I wrote out the image, having finished it. In fact, in this case, it fits. LSST doesn't guarantee that we'll use fits, but the code that I've not shown you actually insulates you from the I/O entirely. So instead of doing the I/O via, give me that fits file, you say, give me the object that describes this image, wherever you find it, whether it's on a data store or whatever.
And that's covered near the end of the tutorial I posted over here.
I'm not going to go further into that. Okay. That just says that
because of the way we do the source detection, we end up with a list of objects that don't have to be contiguous in memory. It's a bit of a detail, but we can fix that. And having done that, all that, we can look at the outputs. So, here's a piece of code that says np logical and dot reduce. That's just NumPy garbage that says take the logical and of the conditions that there's a bit with an incredibly boring, horrible name called base pixel flag saturated center. That says a pixel near the center of this object is saturated. It's bled. It's over the dynamic range of the CCD. So I want the objects that don't have that problem and have no children. Because having run the deblender, I'm not really interested in the parent object. I'm only interested in the children. So that's the definition of good. And we can go in and look at how well we did. So I didn't run a photometric calibration, but here is a plot of PSF minus aperture magnitude. It's not very good. I'll show you why in a moment. One interesting thing here is if you've been working with modern CCDs, you know that a plot of PSF magnitude against an aperture flux usually turns up like this due to brighter fatter effects in the devices. So that as stars get brighter, they get a little bit fatter because of electrostatic fields within the device. Why don't we see that? The answer is because we've already made a correction for that. One of the things we did early on was correct, in fact, using Pierre Astier's algorithm, more or less, not quite, for the brighter fatter effect. So that's gone. So that's one of the things that we did just without thinking about it. I didn't know Jim had done that actually. Jim had example 1.fix. And when I processed this on the plane somewhere over the Atlantic, I said, ooh, that's not right. What did I do wrong? And I realized that Jim must have run the brighter fatter corrections. The scan is not very good. I'll cut back to that a little bit. Okay, so let's just keep going. So we can now do that. That's just the data. Okay. One of the nice things about this being in Python is I can do something like this. Scroll that up. Don't worry about with this CUDA buffering. That's working around the DS9 bar. It says, for every source in my list that were good, so that's just an array index, then call the dot method or a dot at the position of its centroid that's green if it's detected cyan, if it's detected negative, I can run that, or else it's green. So that says overlay all the objects that satisfy this condition. And if I do that, suddenly, miraculously, and it's true, there are green spots drawn on top of all the objects. Now, that's not a very deep thing, but actually it is. I'll show you an example later where instead of just overlaying the objects, I decided to overlay the chrome radii and the flux radius we use to measure the chrome fluxes. So, because this is all written in Python, in fact, the backend is all written in C++, but you don't know that, you get to use an interactive language like Python as a high-level debugger. I could have said, show me the objects which were galaxies brighter than this magnitude. Draw a box around it. Draw whatever. There are lots of things I can do with that. I'm nearly at the end. Just to make this really ugly, I'll run this one instead. By default, this will set new false. This says, look up all the radii which you measured circular apertures. For each object that's good, with buffering, for each object in good, for each radius, draw a circle of that radius in yellow. So you are going to predict correctly that that made a mess of my beautiful image, and indeed it did. So I've now gone in and drawn the apertures, I did aperture flux in for every object. So that's the simple thing, just to run everything through. Let me just make the photometry a little bit better. I skipped over this phrase up here. I said, just run the defaults. If I change this to be false, I'll then run this block of code instead. And this now said, I scrolled it up too far, make me a config object, run the aperture correction to be, turn on the aperture corrections essentially. And if I now run that, okay, so I can do that, make that back to false, so this, run the code starting here, cell, run all below. We'll rerun all those commands I did in such great agony one by one by one. first plotting, that's going to take a while. I should have deleted that, I don't really want that, perhaps. And we can keep going. There we go. So now, this photometry is significantly better. That's because I turned on the aperture photometry code. Now, I can make it look worse again by, instead of plotting that aperture, I'll plot the default aperture. So, I know what went wrong there. So now I said, plot, instead of a particular radius for a radial flux, this one at 12.0 arc second, don't blame Jim for the names actually. I said, just get me the aperture flux. Now I happen to know that defaults to 3 pixels, which is far too small for data that's this bad. Which is why there's an offset of nearly a magnitude between the PSF and the flux apertures. But that's straightforward, because I can say, when I say aperture flux, I mean 12, neither more nor less. It's a question of who's master that sort of, for those of you who know your English literature. And I've now redefined what I mean by an aperture flux. Why is that interesting? It's because I can do the same thing for centroids, for example. I had a long battle with Dave Monet about centroids. The centroid I'm running here is actually one I wrote for SPSS. I think it's pretty good. Dave complained. So I wrote a Dave compliant one. Dave is Mr. Astrometry in the US. That implemented his algorithm. It ran, I think, about 30 times more slowly. But I can run them both simultaneously because I have this ability to add more algorithms. And I can say, use Robert's one or use Dave's one. And when I did the comparison, I was right and I stopped running Dave's thing. But we have the ability to say, when I mean this algorithm, I mean that. I just turned that on. The aperture flux should now be that. If I now run this by hand, long. Why is that taking so long? I don't know why it's taking so long. Along. And now, delete that. And if I now run this, you'll see that the aperture flux has now become reasonably well behaved, and I'll get back to this. It's still not as good as it should be. And you can make this better your very own selves. Because if I go to the README in the Belgrade 2016 blog, it says, when I have shown you this stuff, you can go and mess around with the configurations. So one thing you can do is you can poke around inside this notebook. It should just run and show you the inventor. This one has the bits and pieces in it to change the PSF estimator. And in fact, that tightens up the photometry a bit. Because PSFX is better than my Sloan-based PCA thing. Not a lot better, but it's better. Or you can run this one, in which case you'll get a chance to fiddle with the detection algorithms. And I think it'll end up by zooming into a bright star and demonstrate the effect of really throwing away all the junk around it. Or you can say, I'm really interested in running chronophotometry, which I didn't enable here. So how do I turn that on? So I'm going to stop talking. I'm going to let each of you decide what you want to look at. I'm going to circulate around, and Jim's going to circulate around, and Merlin, I hope, is going to circulate around and clap as you all demonstrate how clever you are running this stuff.
Robert, I'm
Yeah.
tentatively assert that you would not push to a latest notebook to master because the one that I pulled is missing import statements for like database and AFW display.
I don't think that's
Mine as well.
Well, they don't just run. I mean, there's just you fail to import things.
okay.
So,
That is a problem. It's not because I haven't pushed the latest one. What the?
I got them like 5 minutes ago.
This is what I sent them to you earlier, Jim. I know what happened.
I had to import if W displayed
And
by
database.
myself, and also
I
I'm
did
not
that.
sure where to
Okay.
import that base from.
You shouldn't need to.
Sorry, I know that's my fault. I'll push this one. And that base is in there too.
And database.
That's good.
But then I run into, I think maybe my stack is too new. Do you expect us to run on?
I I expect this to run on,
You expect this to run on 12.0 RC1?
yes.
Okay, because I'm getting characterized image class takes these two arguments and you're only giving it one.
I'm looking that up now.
My apologies. Let's fix that. I'll push this thing. Okay, which one do you? I'm going to pass it to her. Can you show me here?
So after the display interface, I'm getting this one. Characterized image class takes these two arguments.
Okay, yes, I don't know if this is,
But I mean, other people may have something.
I think if you pass none, you'd be okay.
this is because I didn't have it. Okay.
Oh, no, but I should be doing that.
Yes.
You should run. Non-common. Yeah, that works. Alright, I'll keep running through.
Okay, you're cool. Sorry about that, everybody.
So, full one.
Yeah,
We have better than that.
I'm gonna open
yeah, no, but in the meantime, you can
Fine,
make it
okay.
work.
passing none to the characterized image constructor should work just fine.
Okay, did that. Can you, do you have everything running?
Have not checked.
Okay, so I push those fixes, you should be able to do a difficult and then run the processing one, and I'll fix the others in semi-real time.
Oh, you didn't push the none, but it works if you do it.
Okay.
You push the import. It's fine, this is working.
Yeah, that's going to help.
Okay. Does anyone need help?
If somebody wants to borrow my laptop, that's not a
Okay, this, yeah, that's the tech. One of those. So there are there's like now 5 different ways to install the software. Oh, probably the easiest.
I must have some reports and doc files.
I don't know. I mean, he's trying to find it. He says he's installed it, but he doesn't know where it is. That's what I said. I wanted to find it from the terminal. He opened like a GUI, and it was like there's nothing that says like the stack in the GUI. But I figured there must be somewhere on his path.
Usually like home directory / miniconda or something. Okay.
Anyone else wake up where you can measure it? Everyone else is
Ako želiš imati tu naredbu, onda moraš instalirati taj način. I kako dok statiš na instalova, CD dok statiš na Windowsu, sam kad tu moraš znati kako se zove, a tamo CD. Sad možeš se sad kažete da ti je visoka temperatura, znači dok god si na 53 možda tebi bude kuće namilina, ali to nije opasna temperatura. To je kritika. Ako ti se nekad isključi, ne znaš zašto. Onda se samo, onda sljedeći put čim ga reportaš, onda ga pita za temperatura koja se desi. Istraživanje na
You were talking about Brighton back.
Dobro, ja sam kupujem Asusa obično, jer jeftini za dobre performanse, ali s jeftinoćom dobiješ lošu moje koštao oko 4500 kuna
That's my rule.
ali isto ima koristica, se jezgra, LSST SSD kao hard disk, pun, tako se prosto zapravo.
That's what that is, the library of
Mikovi su dobri, zapravo su visoki izrazno sa baterijama slušaljaka, ja ne znam koji je to ali to je problem, imaš ovako hard disk, kad ga nikad ne samo bez obzira kaj se mi ispadaš. Ali u principu. to je neki način. A sad sve podatke, ono kad zovemo task manager, Windows, to je sistem sad stisneš i sam napišeš
Yeah, so, the problem, so, when you install the download that's different. You're still downloading. This is
isključit ću kameru i ono, kao to je to, pošto nema danas više ništa. Čekaj, se čuje sad ovo što ti ja sad pričam? Ništa, znači da bude nešto.
Otherwise, when we have 2 minutes to talk,
Hoće, neka stoji. Neka stoji, da.
We found